Thank you, and I'm excited today to talk about the OmniTable query model, which is a new debugging paradigm that treats an execution of a program as a large database table that you can then query using SQL to debug your software projects, and I'll show how that simplifies and accelerates your debugging tasks. Now, throughout this talk, I'm going to follow a developer named Diane, who works on an application that deploys an in-memory cache to accelerate operations that are made to a backend database. Like most software projects, Diane's deployment contains bugs that can lead to failures. And in this talk, I'm going to follow a case study of a bug that was based on a memory leak found in Redis. In Diane's particular case, this memory leak causes the throughput of her deployment to decrease over time, because as she notes, there's an increase in the number of requests that reach and have to be processed by this backend database. Now, this bug is difficult to diagnose because there's many reasons you might see these extra requests. Some of those reasons might not actually even be the result of a bug in the cache. And so the first thing Diane wants to do is confirm whether or not there's even a bug here in her deployment. And to do this, she'd observe the behavior of her cache during an execution that exhibits the particular bug she's interested in. And in particular, she's going to track the number of unique cache items that are accessed within a sliding window of requests, which is also known as the working set size. Now, if she sees that that working set size increases over time and ultimately eclipses the capacity of her cache, then those additional requests actually should reach the backend, so that wouldn't indicate that there was a bug. On the other hand, if the working set size stays below the capacity of her cache, either staying the same over time or even decreasing, then that would indicate that there's a bug in the cache that impedes this efficient behavior, and so that's the cause of the problem. Now, there's lots of ways she could try to track this and calculate this, but probably the easiest way is just to modify the source code of her application. And to do that, she'd start by creating a queue object to track this sliding window over time. Within each call to the function getItem, which is the function that's called by the cache to actually get an item from an in-memory dictionary, Diane would add logic to update this sliding window. And then finally, she'd compute the unique keys within that sliding window by using a set operation before finally printing out the size of that set. The problem here is that determining the unique keys is a linear operation over this relatively large queue. And as a result, computing this debugging logic can come with high overhead. In fact, it's not unusual to see sophisticated debugging computation, not unlike this one, impose slowdowns that are an order of magnitude, up to even many orders of magnitude, that basically preclude the use of those tools altogether. Well, in this case, Diane can actually solve the problem by adding a dictionary to track the unique keys in that window over time. The issue here is that this adds significant complexity to her debugging, since Diane now needs to ensure that these two different data structures remain consistent, and she has to do that by adding all of this nested control flow logic and deep complexity. A single bug in any of this logic would lead Diane to the wrong conclusion when she tries to understand what's going wrong. To make matters even worse, over the course of a single debugging session, Diane's going to have to ask a lot of additional follow-up questions, and she's going to have to construct and execute all of these additional programs. Each time she does that, she has to face this high performance overhead and this high programming complexity. Okay, so what have we learned over the last few slides? Well, I showed that Diane needs to contend with high programming complexity and high performance overhead when she's using traditional debugging techniques that support procedural-like interfaces. And these include most of the things you probably use, things like GDB or printf debugging. Now, to combat these issues, of course, the community has proposed a number of debugging tools. But unfortunately, we observe that they all prioritize one of these metrics over the other, and as a result, they retain at least one of these limitations. For example, there's been some tools that lower performance overhead by employing really low-level reasoning. And it's great, it really improves performance, but the problem is that if Diane actually tries to apply one of these tools in a random debugging session, it's going to be very difficult for her to do so. On the other end of the spectrum, there's a lot of tools that do the opposite. They reduce programming complexity by turning to declarative languages, but they retain this high performance overhead. Moreover, these existing declarative tools have another limitation. Most of them expose an incomplete interface. They prevent the things that Diane can observe about her execution when she tries to go debug it. And as a result, we find that in many cases, for example, in this performance degradation, these tools are insufficient. They don't allow her to do the things she needs to do in order to understand what's going wrong. Well, in this talk and in this work, we propose a new model that we call the OmniTable query model that simultaneously reduces programming complexity and decreases performance overhead without having to make restrictions on the execution state that Diane can observe. The key abstraction, and at the heart of the model, is this thing we call an OmniTable that provides an all-encompassing database table representation of an execution that exposes every single byte of user-level state that's reached during that execution. Conceptually, what happens is an OmniTable is extracted as your program executes. And then later on, Diane can debug that execution by querying the OmniTable associated with that execution by using SQL queries. By exposing all execution state as a large table that can be queried with a high-level language, the OmniTable reduces the programming complexity of debugging without placing restrictions on what you can observe. Our evaluation shows that the OmniTable debugging logic required across a number of case studies can be written up to 15 times faster than the same or equivalent debugging logic expressed in the procedural tools that you're probably used to using today. Moreover, by decoupling execution from debugging, SteamDrill, which is our prototype system that actually implements this model, is able to resolve OmniTable queries on average by 95 times faster than those same existing tools. So in the rest of the talk, I'm first going to talk more about the OmniTable query model, or describe what it looks like, and hopefully give you a sense for some of the complexity comparison and the wins that we're seeing. At different points during this first half of the talk, you might be thinking, well, is any of this actually feasible? And what I want you to do is suspend disbelief. Assume that it's all possible. And then in the second half of the talk, I'll bring this back down to earth and explain how we're able to actually achieve and realize this vision when I described SteamDrill, before finally talking about how it performs. Okay, so let's start with the OmniTable query model. So as I mentioned, at the heart of this model is an OmniTable, a table representation of an execution that includes all of the architectural state of that execution immediately before every single executed instruction. And there's going to be a separate row in this table for each of those instructions. So what do I mean by all of the state? Well, I actually mean all of the state, like the value of every byte of memory, the value of every single register, and maybe some metadata, like what's the thread that executes the next instruction? What's the time that each of those instructions occur? Okay, so all the execution state is contained in this table. I think you probably will agree. But it might as well be inaccessible, because Diane would now have to express debugging in terms of individual bytes of memory and individual registers. So the model uses database concepts to build up higher-level abstractions on top of this table. And I encourage you to see the paper if you're interested in understanding exactly what that looks like. But the net effect is that the model allows Diane to reason about her program's execution using derived views on top of the OmniTable, such as the functions view, that shows information about all the functions executed over the course of that execution, or maybe the stores view, which shows information about all of the store instructions that were executed throughout that execution. Now, conceptually, this is really where we differ from past work. So the OmniTable is taking this bottom-up approach of building abstractions using this relational modeling, whereas prior tools took a top-down approach of essentially predefining a few views. And so that's where they're sort of inherently incomplete. Okay, then to actually query these tables, as I mentioned, Diane can write SQL queries over maybe the derived views themselves or over the OmniTable itself, and she can in fact join across those two different views as well. So she can pick and choose. Okay, as an example of how this actually works, I'll next walk through how Diane could express that first debugging question I talked about in the beginning of this talk for the throughput degradation. So recall that the goal is to estimate the working set size of her cache by computing the unique keys that are accessed during a sliding window. Now, to do this with the OmniTable, she first has to actually extract an OmniTable for her system during some execution that exposes this problem. And then she can write the following SQL query. So the first thing that she does is she uses the functions view to get all of the calls that are made to that getItem function, which, remember, that's the function that actually gets an item from an in-memory dictionary within the cache. For each of those calls, she creates a sliding window containing the 10,000 preceding calls to getItem. And then for each of those windows, she outputs the time of the last call to getItem in that window, just as a way of having a time marker She's going to build a time series here. And then she also counts the number of distinct key arguments within that window. Now, at this point, she can actually plot this data using any of a number of different off-the-shelf tools to, for example, track that working set size over time. Now, if you've never written SQL before, this might seem a little bit daunting. But recall that the comparison was that procedural tool, which required something like a dozen lines of code and a lot of complexity around maintaining multiple data structures. To actually quantify these gains that we're seeing here, we performed 5 case studies by finding bugs that were reported in open source software. We tried to target notoriously challenging bugs, and we constructed the OmniTable queries that would be required to go from the initial observed failure down to the underlying root cause. In the end, we wound up with 15 separate queries across all of these different case studies. For comparison, we produced equivalent logic using GDB's Python bindings, which provide a scriptable interface over traditional GDB abstractions, such as breakpoints. We measure complexity of those scripts and the queries using 3 different metrics: the number of lines of code, the size of the abstract syntax tree, and then a metric called Halstead complexity, which estimates the amount of time it would take to write a program correctly based on properties of that abstract syntax tree. The OmniTable improves complexity across all metrics. Here I'm showing you the geometric mean of the improvement. And most notably, we estimate that the OmniTable queries can be written correctly 3 times faster than current tools that you're probably used to using. Okay, so as promised, I'm next going to talk about how we actually bring this model back to Earth. How do we make this a reality? But before I talk about how we make it a reality, I first want to address, well, what's the core problem that we're dealing with here? The core problem is that a naive implementation, which is like what I've shown on the screen here, is completely and totally infeasible. Because an OmniTable is equivalent to producing a core dump on every single instruction within your execution. And so that would impose way higher overhead than even your most expensive debugging tool. And moreover, it would result in an object that's petabytes, even exabytes in size. So you probably couldn't store it for more than maybe 1 execution or 2 executions. So to solve this problem, our prototype system, SteamDrill, leverages the decoupling between debugging and the original execution that's provided by the OmniTable to defer the work of actually materializing a table until Diane actually wants to observe some particular cell of the original table. We call this technique that we're using here lazy materialization. Okay, so instead of actually extracting the table, SteamDrill uses deterministic record and replay to capture the non-deterministic inputs that are made to that program. Deterministic record and replay imposes single-digit overheads in many cases, and so it can be deployed in testing and potentially even in production environments. So you might be able to query a production environment's OmniTable. Okay, so then later on, when Diane queries this sort of OmniTable that's associated with that execution, SteamDrill converts the query logic into dynamic instrumentation, which it injects into a new replay execution. It's basically treating the replay as a generator for this OmniTable. So this approach provides a feasible implementation of the query model, but if we just did this naively, we'd retain the high performance overhead of existing tools. So SteamDrill leverages the decoupling between execution and debugging, again, in order to enable automated optimizations, which allow it to actually compute debugging queries faster, which is what I promised in the beginning. We've explored 2 such optimizations in this work. The first is that rather than resolving each query with a single replay, SteamDrill employs a novel multi-replay execution strategy in which it decomposes query logic into small operators and then schedules them across potentially many replays. This allows it to use inexpensive to calculate data from a query to filter data that would otherwise be very expensive to calculate. So for example, the query on this slide has 2 views, and SteamDrill would use multi-replay resolution to compute the less expensive to compute view first, use data from that computation to filter out and reduce the portions of the more expensive to compute view that it needs to compute in some later replay. Okay, somehow we actually have to describe and figure out how to assign these tasks across replays, and we do this by using a pretty standard database optimization workflow in which what we really are doing is using the join algorithm that's assigned during query planning in order to guide the number of replays that we use. We describe that algorithm in more detail in the paper. As promised, we've also explored other optimizations, and the main one that we've been looking at is the ability to use large cluster scale parallelization to parallelize the tasks of instrumentation and the re-execution of the replay across thousands of cores for each of these different replay stages. Okay, so that's all I'm going to talk about in terms of the design overview for SteamDrill. I next want to go through how it performs on real queries. So we evaluated it on 3 representative queries from our original use cases. We're choosing queries that vary greatly both in the views that they use and the time that we take. Most notably, all the way on the right-hand side, there's a query that takes almost 2 days to compute using current tools. In this plot, we're showing latency on the y-axis, which is shown in a log scale, and lower is better. We compare GDB latency, SteamDrill when we run on a single core, and then SteamDrill when we run on 64 cores. And our results show that SteamDrill queries can be calculated nearly 2 orders of magnitude faster than these GDB counterparts. We dive deeper into the design decisions and novelty that enable this in the paper. Okay, so in conclusion, today I told you about how the OmniTable abstraction treats a program execution as a large database table that you can then query using relational logic. I showed you how this model allows us to simplify debugging logic by up to a factor of 15 when we compare that to our standard debugging tools. And then I talked about how our prototype system, SteamDrill, leverages lazy materialization to accelerate the calculation of OmniTable queries by a factor of 95 on average when compared to those standard debugging tools. In this slide, there's some QR codes. You can check out the paper and the source code on GitHub, as well as there's my contact information. I'm happy to talk about all things OmniTable. I look forward to taking your questions, and I'll be in the hallway later if you want to chat too. Thanks.